Far beyond our blue planet, past the pull of the moon, a telescope drifts in silence. It circles a point in space called L2, a calm region where the gravity of the Earth and the Sun almost balance. There, about 1,000,000 miles from home, floats the James Webb Space Telescope. It does not look for brightness. It listens for warmth, for invisible light called infrared. Every photon it gathers began its journey years or even centuries ago. When that ancient light touches Webb's golden mirrors, the story begins. Among the stars it studies is a small red sun in the constellation Leo. To our eyes, that star would be invisible. But in 2015, NASA's Kepler telescope noticed something unusual. Every 33 days, the star dimmed for a few hours, then brightened again. That repeating flicker meant a planet was passing in front of it. A distant world now known as K2-18b. K2-18b is about 2.5 times larger than Earth and around 8 times heavier. It orbits its faint red star at a distance where the temperature could allow liquid water. Astronomers call this region the habitable zone. Not too hot, not too cold. The star itself, named K2-18, is a red dwarf, smaller, cooler, and longer-lived than our Sun. Such stars can shine steadily for trillions of years, but they sometimes send out flares of radiation. Any life near them would need thick air, strong clouds, or deep water to survive those bursts. Between 2015 and 2019, telescopes studied the starlight that passed through K2-18b's atmosphere. When the planet crossed its star, a small amount of light filtered through its gases before reaching us. In 2019, the Hubble Space Telescope found a trace of water vapor in that light. It wasn't proof of oceans, but it was a first clue. Water in the atmosphere of a planet that could be mild in temperature. Then came Webb. Launched in 2021, it began its work the following year. Its mirror is 6 times larger than Hubble's, and tuned to read the faint heat of faraway worlds. When Webb observed K2-18b in 2023, it recorded patterns in the starlight, tiny dips and rises that act like fingerprints of molecules. From those patterns, scientists detected methane and carbon dioxide. These are common gases, but their combination was interesting. On Earth, methane often comes from living things, while carbon dioxide can come from both volcanoes and life. The balance between them can reveal how a planet breathes. Webb also found very little ammonia, which fits certain models of planets that might have water below their clouds. Some researchers began using a new word, Hycean world, a planet covered by a hydrogen-rich atmosphere and possibly an ocean beneath. It sounded promising, but scientists were careful. The data did not prove oceans or life. It only suggested that such a model fit what Webb saw. A few months later, another detail appeared in the data. A faint, uncertain signal matched a molecule called dimethyl sulfide, or DMS. On Earth, DMS comes mostly from ocean plankton. The idea that such a molecule might exist on another world was thrilling, but the signal was weak. NASA and the European Space Agency quickly explained that the feature was not confirmed. It could be a coincidence, noise, or another molecule entirely. More observations would be needed to test it. Even without certainty, the discovery was remarkable. Webb had measured the atmosphere of a planet 124 light-years away. The light it captured left that world around the year 1900, before airplanes, before radio broadcasts, before modern astronomy itself. Think of what that means. Those photons traveled through space for more than a century, untouched, until they reached a mirror no bigger than a tennis court floating in darkness. Inside them was information about a planet orbiting a quiet red sun, a world we cannot see, but can now describe. The picture is still incomplete. K2-18b may have an ocean, or it may be a deep ball of gas. It could be calm or stormy, habitable or not. What we know for sure is this: light from that planet carries the story of its chemistry, and Webb has learned to read it. So, as the night settles, remember, we are listening to a world that circles its star every 33 days, in a sky you can point to in Leo. A world far older than our questions, a planet that shows how far curiosity can reach. When a planet passes in front of its star, it leaves a signature in light. A tiny part of the starlight travels through the planet's atmosphere before it reaches us. Each gas in that atmosphere absorbs light at specific colors, like notes on a scale. When scientists spread that light into a spectrum, they can see which colors are missing. Those missing lines reveal which gases are present. This is how the James Webb Space Telescope studies worlds it cannot see directly. It waits for the moment when a planet crosses its star. It measures the brightness before, during, and after that crossing. Then it compares the results. The difference between them shows what the planet's air is made of. For K2-18b, Webb repeated this process many times. Each observation lasted hours, collecting light that had traveled more than 100 light-years. The planet is so faint that its signal is less than a millionth the brightness of its star. Even with Webb's precision, the data had to be combined and cleaned to remove noise. When the results came back, they were unmistakable. Webb had detected methane and carbon dioxide. Both are carbon-bearing molecules. Both are vital clues to a planet's chemistry. On Earth, methane is produced by volcanoes and by living organisms. Carbon dioxide comes from both geological and biological sources. Scientists ran computer models to test what kind of planet could produce those gases in those amounts. The models that fit best suggested a world covered in hydrogen, with a possible layer of water below the atmosphere. That led to the idea of a Hycean world, a planet with a hydrogen-rich atmosphere and an ocean beneath. If this is true, K2-18b could have conditions stable enough for chemistry similar to life. The thick hydrogen blanket would keep temperatures mild and protect any ocean from the star's radiation. The balance of gases would remain steady for millions of years. That kind of stability gives chemistry time to evolve. But the scientists were cautious. Many other explanations were possible. The same data could also fit a world with no ocean at all, just a thick envelope of gas around a solid or icy core. If that is the case, the planet might not have a surface where life could exist. Then came the faint signal of dimethyl sulfide, or DMS. It was only a small dip in the light curve, barely above the background noise. On Earth, DMS is released by microscopic life in the ocean. If confirmed, its presence would be extraordinary. But the Webb team made it clear. This was not evidence of life. The detection was uncertain, and other molecules could produce the same signal. In science, a single observation is never enough. To confirm DMS, Webb would have to see the same feature again during another transit, with instruments tuned to different wavelengths. Until then, the idea remains a possibility, not a discovery. The process of verification is slow and deliberate. Scientists review every step. They check if the telescope's instruments were stable. They make sure cosmic rays, star spots, or temperature changes did not distort the readings. Other teams around the world analyze the same data to confirm or challenge the results. Only after that can a finding be accepted. Webb's sensitivity has changed what is possible. For the first time, we can measure the atmosphere of a small planet in a habitable zone. Before Webb, only massive gas giants near their stars could be studied in detail. Now, worlds closer to Earth's size can be analyzed too. Even if K2-18b turns out not to host life, it has already shown that detecting complex atmospheres is possible. The data will guide future missions, such as the European Space Agency's Aerial Telescope and NASA's upcoming Roman Space Telescope. Together, these observatories will build a library of exoplanet atmospheres. From that, scientists can begin to understand which types of worlds are common and which are rare. Back on Earth, researchers continue to refine their models. They simulate the conditions inside K2-18b's atmosphere, changing temperature, pressure, and composition. Each variation helps them see how methane, carbon dioxide, and water behave together under alien conditions. Some models produce simple gases only. Others create complex organic molecules. The building blocks of life. Every step is a lesson. Even when the result is negative, it tells scientists where to look next and what to expect. Science is not about instant answers. It is about narrowing possibilities until only truth remains. So, the story of K2-18b continues. A planet passes in front of a quiet red star every 33 days. A telescope far from Earth listens patiently, and from that faint signal of light, we are learning not just about that distant world, but about the power of observation itself. If we could see K2-18b with our own eyes, it would not look like Earth. Its light would be tinted red, not blue. The reason is simple. The planet's star is a red dwarf, cooler and dimmer than our Sun. Its glow gives the entire world a deep copper tone. The planet is much larger than Earth, yet smaller than Neptune. It may have a thick hydrogen atmosphere that stretches for hundreds of kilometers. The air there would be heavier and denser than anything we breathe. If you tried to fly through it, the drag would feel like moving through warm liquid. Scientists believe that one side of the planet always faces its star, the same side in constant daylight, the other side trapped in endless night. This happens because of tidal locking, the same effect that keeps one face of the moon always turned toward Earth. On the day side, the red sun would hang in one fixed spot in the sky. It would never rise. It would never set. The light would be dim but steady, casting a soft orange glow across the clouds. The temperature might stay around 50 degrees Celsius near the upper atmosphere, warm, but not scorching. If the models are correct, below those clouds could be a vast global ocean. The atmosphere above it would contain methane, carbon dioxide, and water vapor. Winds would move slowly, spreading heat from the bright side toward the dark. Far below, pressure would increase until the air itself turned into fluid. We do not yet know whether the ocean is real. Some models predict it. Others suggest the lower layers are too hot and dense for liquid water. The truth is hidden beneath thousands of kilometers of gas. Our instruments can only study the uppermost layers, where light can pass through. Everything deeper is guesswork, guided by physics. Still, the idea of a Hycean world captures the imagination, a planet where the sky and sea blur together, where rain might fall in slow motion and dissolve before it touches the surface, where no land exists, only endless liquid plains under an unmoving red sun. The air there would not be breathable. It would be mostly hydrogen and methane, too light and thin for human lungs. But the chemistry within it could be active. On Earth, such environments produce rich organic reactions. Molecules form, break apart, and reform again. In warm, stable conditions, those reactions can grow more complex over time. If life exists there, it would not look like anything on Earth. There would be no trees, no fish, no oxygen. Perhaps only microscopic organisms drifting in the upper haze, feeding on chemical energy rather than sunlight. Even that is speculation. Yet the physics does not forbid it. And in science, what is not forbidden is worth investigating. Some scientists prefer a simpler view. They argue that K2-18b is not a water world at all. They say it is a mini Neptune, a planet made mostly of gas, with no ocean or solid surface. In that version, the temperature and pressure increase continuously downward, turning the air into strange, dense fluids. No place to land, no place to swim, only a smooth transition from vapor to liquid to ice deep inside. Both views fit the data. Both could be true in part. The challenge is that we only see what happens where light escapes, the edge of the atmosphere. Webb's instruments can tell us what gases are there, but not exactly where they are or how deep they go. That is why future missions will try to measure temperature and pressure profiles directly. Even with uncertainty, scientists continue to imagine what it might feel like to stand, or float, inside that alien air. Above, a red sun frozen in the sky. Around, a soft orange mist glowing with infrared light. The horizon faded into haze, the ground invisible. Every sound muffled. Every movement slow. If K2-18b has an ocean, its color would not be blue. The thick atmosphere would scatter light differently. The sea might appear gray, violet, or even black. Yet it would still move with waves, driven by the planet's rotation and the faint heat of its star. The quiet would be complete. No wind sharp enough to roar. No thunder, only the deep hum of pressure and the steady warmth of a star that never sets. This image may sound poetic, but it is built from facts, from equations of light, gravity, and chemistry. Each line of data from Webb refines that picture. Each observation narrows what could be true. That is how imagination and evidence meet. What matters most is not whether K2-18b has life, but that it could have conditions suitable for life. It shows that such planets are not rare. They may orbit many red dwarfs across the galaxy. Each one is a laboratory where nature runs experiments in chemistry that have lasted for billions of years. The next time you look at the night sky, remember this. Somewhere in the direction of Leo, there is a small red star. Around it moves a planet wrapped in hydrogen and mystery. The light from that world left long before we were born. Now it tells us that even far away, nature may follow familiar rules. Gravity, temperature, chemistry, working quietly, patiently, in places we may never reach. When scientists look at a world like K2-18b, they are also looking at themselves. Every discovery beyond our solar system is a mirror, reflecting how far curiosity can reach. The light from that small planet teaches us not only about its chemistry, but about our own desire to understand. The story of K2-18b is one of patience. Each piece of data is a fragment. It takes months, sometimes years, to collect enough fragments to form a single picture. Nothing about this work happens fast. But speed is not the goal. Accuracy is. When Webb detected methane and carbon dioxide together, it gave astronomers confidence that we can now measure the atmospheres of small planets. Just 10 years ago, that was impossible. Back then, telescopes could study only large gas giants close to their stars. Now, for the first time, we can analyze a world only a little larger than Earth, orbiting within the zone where water might exist. That is progress measured in patience. Each discovery like this also reshapes our understanding of life. For centuries, humanity imagined that life could exist only on worlds like ours. Blue oceans, white clouds, yellow sun. But the data from K2-18b suggest otherwise. It shows that chemistry favorable to life might occur under completely different skies, under red light, in hydrogen air, maybe deep beneath layers of cloud. That realization expands what we call habitable. Life might not need to look like Earth's life. It might not need oxygen. It might not even need sunlight. It may exist in shadows and pressure, drawing energy from reactions that occur quietly, without flame or spark. Still, scientists remain careful. They know how easy it is to mistake curiosity for conclusion. Many discoveries in the past were announced too early, only to fade when new data arrived. This is why Webb's team insists on precision. The DMS signal, if it exists at all, must repeat in later observations before anyone can call it real. This discipline, this refusal to rush, is what makes science reliable. It protects truth from wishful thinking. It allows us to stand on solid ground, even when studying worlds we will never visit. The philosophical side of these findings is just as deep. If life exists elsewhere, even in simple microbial form, it changes how we see ourselves. It means life is not an accident. It is a natural result of physics and chemistry, given enough time and stability. In that view, the universe is not empty. It is alive with potential. But even if K2-18b turns out to be lifeless, the search itself is meaningful. It reminds us that exploration is not only about discovery, it is about the act of looking, the courage to ask questions without knowing the answers. When humanity points a telescope into the dark, it is an act of trust. Trust in reason, trust in evidence. This perspective also brings humility. The light Webb captures began its journey long before any of us were alive. When those photons left K2-18b, humanity was still discovering flight. When they reached us, we had built a machine capable of reading their stories. The distance between those moments is filled with everything we have learned. And as we read those stories, we are reminded that Earth, too, is fragile. Its thin atmosphere, its balance of gases, its warmth, all of it depends on chemistry and distance, just like any other planet. Studying exoplanets is not only about them. It teaches us how special and delicate our own home is. The same equations that describe light from K2-18b describe the carbon in our air and the water in our clouds. When we learn to understand other worlds, we are really learning to understand ourselves. Every measurement Webb makes feeds into a larger picture, a comparison of hundreds of worlds. Scientists call it comparative exoplanetology. By comparing many planets, they can see patterns, which molecules appear often, which are rare, and how stars influence their planets. K2-18b is one point on that map. There will be many more. In laboratories on Earth, researchers recreate similar conditions. They fill chambers with hydrogen, carbon dioxide, and water vapor. They adjust temperature and pressure to match what models predict for K2-18b. Inside those chambers, chemistry happens on its own. Molecules form, combine, and evolve. Some create simple organic compounds. Others remain stable gases. Each test helps scientists interpret Webb's data more accurately. Even philosophers and artists find meaning in this work. The discovery of planets like K2-18b invites us to think about connection, about how life, if it exists, might be a universal story rather than a local accident. It suggests that the universe itself may be a kind of laboratory, constantly experimenting with ways for matter to become aware of itself. For the scientists who study these signals, the emotional connection is real. They spend long nights adjusting models, checking calibration, writing code. Then one day, after weeks of analysis, a pattern appears. A line on a graph, a tiny dip in brightness. It is the fingerprint of a molecule on a world no one has ever seen. In that moment, distance disappears. The planet feels close, almost familiar. Each discovery, no matter how small, adds to a shared human story. We are a species that looks up. We have always done it. From the first firesides to the space age, Webb is just the newest way to continue that gaze. It gives us light turned into knowledge, and knowledge, when shared, becomes wonder. When people ask why we spend so much effort searching for life elsewhere, the answer is simple. The search for life is really the search for meaning. To know that the universe can make life more than once is to know that existence itself is generous. And even if we never find that second spark, the act of looking teaches us to value the first, the one here, on Earth. The story of K2-18b does not end with discovery. It continues quietly, orbit after orbit, as new light reaches us. Each time the planet passes in front of its small red star, the James Webb Space Telescope listens again. It collects more data, sharpening the picture, confirming or correcting what we thought we knew. Science is patient. Every new observation tests the last one. If the signals repeat, the finding becomes stronger. If they vanish, the models must change. Nothing is certain until it holds steady over time. That is the rhythm of real discovery. Even if K2-18b never shows signs of life, it has already changed what we can do. Before Webb, a planet this small and this far away could not be studied in such detail. Now, its atmosphere, hundreds of trillions of miles distant, can be measured and analyzed. That alone is a milestone in human history. The methods developed through this research will guide future missions. The Aerial Telescope in Europe and NASA's Roman Space Telescope will soon join the search. Together, they will observe thousands of planets. Each one will add another piece to the puzzle of how worlds form, how they evolve, and how often they create conditions suitable for life. From those thousands of worlds, patterns will emerge. Some will be rich in carbon. Some will be dry and empty. Others might have clouds and chemistry similar to Earth's. Over time, we will begin to understand whether our planet is rare, or whether life's ingredients are spread across the galaxy like dust in sunlight. The search is not about proving that we are not alone. It is about learning how far nature's creativity can go. If life appears elsewhere, even once, it will mean that the universe tends toward it naturally. If it does not, that silence will still teach us how extraordinary our own existence is. Both answers are worth finding. For the scientist studying K2-18b, the reward is not fame or fortune. It is understanding. Each graph and each equation tells part of a story that began long before humanity existed. They are listening to the afterglow of creation, still echoing across space. When the data from Webb arrive on Earth, they come as streams of numbers. To most people, they look meaningless. But to a trained eye, they are music. A pattern of brightness and shadow that speaks of temperature, gas, and distance. Behind those numbers lies a world, a real one, a planet orbiting a faint red star in Leo, 124 light-years away. Right now, as you listen to the story, the telescope continues to orbit the Sun with Earth. Its mirrors stay cold and still, protected from heat by its great silver shield. The red dwarf K2-18 shines softly, invisible to the naked eye, but constant. And the light from its planet, the same light Webb has studied, continues to travel outward through space. That light began its journey more than a century ago. It will keep moving long after we are gone. Someday it may reach another telescope, built by people who have yet to be born. They will see what we saw. They will ask new questions, and they will find new answers. This is what science really is. A conversation across generations, carried by light. Each discovery is a message passed forward in time. Webb is our voice in that conversation, speaking to the future through the language of stars. The search for life continues. Perhaps one day a telescope will capture unmistakable proof, a chemical imbalance so perfect that no process but biology could explain it. When that happens, humanity will look up at the night sky and know that we are part of something vast and shared. Until then, the stars remain quiet, but not silent. Their light still reaches us. It brings knowledge and with it, peace. The universe is not cold emptiness. It is filled with stories waiting to be read. K2-18b is only one of them. A small planet orbiting a red sun, hidden in Leo. A reminder that even in darkness, there are signals. Even in distance, there is connection. And even in silence, there is meaning. So as the night settles, take a moment to look up. Every point of light you see is a star with its own planets, its own chemistry, its own story. Some may hold oceans. Some may hold dust. All of them hold the same laws of nature that shape our world. The next time you see the stars, remember this. The same universe that made them also made us. The same physics that moves those planets moves the atoms in your body. We are not separate from the cosmos. We are part of it, built from the same dust, shaped by the same light. The James Webb Space Telescope continues to listen. The planets continue to circle their stars. And we, on our small world, continue to wonder. Sleep well, traveler. The universe is awake.